So today we are doing scalars and vectors. Right, now this is a fundamental topic and I am going to start off with whiteboard and across. Right, so scalars and vectors. Normally at this point I would go through the specs and say which specs have got this in and which haven't. They all have this in. Every version of physics that you do has scalars and vectors in. You can't escape from them. They are a fundamental idea. So we've got the definitions then. Okay, so a scalar, it's a thing that can vary, so a variable which has size only. And sometimes we would talk about, instead of talk about size, we would talk about magnitude. Okay, and a vector, it's a variable again. And it has size, magnitude, and direction. So vectors are indicated by arrows. So here is a vector. The length of the arrow indicates the size of the vector. So the length is equivalent to the size, and the direction of the arrow indicates the direction of the vector. So scalars and vectors are both of them variables, but vectors have both magnitude and direction, whereas scalars just have magnitude. They just have size. Now, just to confuse the issue, there are one or two things which are sometimes referred to as pseudo vectors. So, for example, time. So time, I mean, people talk about the arrow of time. Time has a direction, sort of. So we talk that time, it's sometimes considered a pseudo vector because it has a direction, but you can't actually reverse direction. It's just forwards or backwards. So it's only and clockwise and anti-clockwise when you're talking about spinning things. That's a pseudo vector. Okay, it's not a real proper vector. So yeah, it's only a pseudo vector. Okay, I'm going to write that down. P-S-E-U-D-O vector. Okay, like spin direction is also a pseudo vector. So it can only be plus or minus. So it hasn't really got a direction, but people, well, anyway, I don't know. So I would, pseudo vectors are not part of your course, so you haven't got to identify them. You only have to identify things that are clearly scalars or clearly vectors. Right. Okay. So now what I want is, let's see if you can give me some examples, please. Okay. So oh, do we get marks for stating time as a vector? No, don't mention time. It's just too confusing. Okay, so yeah, very good question to ask because now it's clear to everybody. I mean, you know, yeah, just don't mention it. I wouldn't bother. Okay, so scalars then. Okay, and vectors. Can I have Oh, KB wants to go through it again. Okay, so the definition of a scalar is a variable, something which can vary, that has just size. That's okay. And vectors are things that have both size and direction. And vectors are represented by arrows, and the direction of the arrow indicates the direction of the vector, and the length of the arrow indicates the size or the magnitude of the vector. Right, so now what I want is, please, some examples of scalar variables. Can anybody give me an example of a scalar? Energy, excellent. Energy. Mass, very good. Speed, very good. Anyone for any more? So well done to you three. Fantastic. Distance. Good. Temperature. Yes. Okay, I'm going to go with time. Yeah, why not? Time. Oh, time. Oh, that stopped to save or something partway through. Okay. Any others? Okay, that'll do for starters. I want some vector, please. Vectors. Now, acceleration. Oh, yes. Momentum. Yes. Velocity. Yes. Displacement. Yes. Weight. Okay. Weight is one of a whole family of vectors which we call forces. Yes. Okay. Um, okay. Right now, you've given me the year 12 versions of vectors. There are some others, okay, and I want you to be aware of them. Even though you're in year 12 and you won't have to deal with these until year 13, but the gravitational field strength. So, gravitational field strength. It has an arrow associated with it. It's a vector. Guess what? Electric field strength. Come on, give me the last one. Magnetic. There we go. Yeah. Okay. And of course, all the forces. So all of the forces with all of the different names that forces can have. So tension and friction and up thrust and so on. I mean, they all of them are vectors. Okay, that's excellent. Right now, I'm very, very pleased that between you, managed to get distance as a scalar and displacement as the vector equivalent. Speed as a scalar and velocity as the vector equivalent. That's really, really good. Right now, the other thing to notice here is we've got momentum. I'm going to point out this one. Okay, so momentum there. Momentum, of course, is actually two things multiplied together. Okay, can anybody tell me how you get momentum? What's the formula for momentum? Yep, it's mass times velocity. Well done, Ludan. Okay, so momentum is given the symbol little p, just to confuse it with pressure. And it is mass times velocity. Now, I want you to notice something that mass, can you see, is actually a scalar, but the velocity, that bit, is a vector. And this formula, scalar times vector, well done, Ekjot, scalar times vector, that combination is a vector. Okay, so you need to be aware that if you multiply a vector by a scalar, you get a vector. Okay, so I'm going to write that down. A scalar multiplied by a vector gives a vector. Right now, one of the other scalars that you told me about, where's my thing? There it is this one. I'm going to change color. That one. Energy. Okay, what's the equation for energy? Can you give me the equation for energy? Oh, okay, power times time. Yeah, I was thinking about kinetic energy actually. Um, Power and time are not, neither of them vectors. So yeah, half mv squared. Yeah, absolutely. You've got it. So we've got a half times mass times velocity squared. And of course, mgh is potential energy, gravitational potential energy, and you're quite right, power times time is energy. There are lots and lots and lots of different expressions of energy, so I should have been more explicit. Now I want you to notice again, right? I better go back to my red, hadn't I? That is a scalar. Of course, the half is just a number, so that's also just a scalar. And what have we got here? This is actually, I'm not sure that you can call a half a scalar because it's not a variable. So I don't think you can call numbers scalars or vectors. Now, this is, of course, a vector. But what are we doing to it? Can you see that we're squaring it? Now, when you multiply a vector by another vector, you lose all direction. So it is no longer a vector. So in effect, we've got a scalar multiplied by scalar, which gives us a scalar. Okay, so this is a scalar multiplied by a scalar, whoops, gives a scalar. And if you have a vector and you multiply it by a vector, you get a scalar. So as soon as you square your velocity, it doesn't have a direction anymore. Would you lose the direction because when you square it, there are no negative values? I guess so. Yeah, actually, I think probably. Okay. So these are the general rules then about scalars and vectors. Okay. Right now, the next thing that we're going to do is we are going to think about what sorts of things we are expected to do with our, well, it's vectors mostly. Scalars is just numbers. We do all the things that we do in maths with numbers. But vectors, because they have direction, we have to allow for the direction. And I'm going to say to you quite forcefully now that drawing diagrams to show what the vectors are doing is a really powerful way of thinking about vectors and getting the answers right. And one of the things that we need to be able to do is we need to be able to draw scale diagrams. Okay, it doesn't actually come up very often, but scale diagrams do come up periodically on the A level, and you do have to, first of all, get the scale right, and second of all, actually get the directions right. So one of the things that I would suggest that you do is get yourself a 30 centimeter see-through plastic ruler and a see-through plastic protractor as well, so that you can draw things to scale if you need to. So the next thing I'm going to do is I am going to draw, let's do an arrow, so that here is my vector. I've drawn a vector and I can resolve that vector. Okay, so this is now moving on from scalars and vectors to the sorts of things that you can do with scalars and vectors. Now I can resolve that vector into two other vectors. Okay, if I do this, I can, oh, let's do that one now. No, I want it to be red. Right, so from there to there, okay, and then I'm going to do exactly the same. I'm going to go from, oh no, I want to do the same again, please. From there to there, okay. So my black vector can be replaced by my two red ones. Okay, so if I call this one A and this one B and this one C, and I draw a line over the top, I'm sure that you've come across this in your GCSE maths. you can say that A, the vector A, is equal to the vector B plus the vector, it really would help if I wrote the right letter, the vector C. Okay, and what I've done here is I've got, can you see a triangle of vectors? So these two red ones add up to give me the black one. Okay, now I can draw the parallelogram of forces. Okay, so if I draw one that's parallel to C, I'm doing this by eye, about like that, and then I'm going to do another one that's parallel to B and the same length. Can you see that it doesn't matter if I do B plus C or if I do C plus B, I still end up with the same answer. So this one's also C, this one's also B. Okay, now all of this is exactly the same as you get in your GCSE maths. Okay, I hope all of this is familiar to you. I hope you can also see that I can take my vector, this one, and I can slide it about. And I can say, well, it's C, it's still C over here, and it's C over here, and it's C over here. But can you see that the angle of my vector never changes? Okay, the length of my vector never changes, but it's still the same vector. Now, if I put it back in my parallelogram of forces, you can see the parallelogram, I hope. The C and the C and the B and the B are the same. Okay, and I want you to realize that you can slide your vectors about. The angles don't change, and the lengths don't change, but you can literally move them about. And that makes it possible for you to figure out what's going on. Okay. One of the things about vectors is if you have an object that is in equilibrium, if you put the vectors that are present there, the force vectors that are present, in a tip to toe formation, so the point of one arrow goes against the back end of the next arrow, then you will get a closed polygon of forces. And that is an indication that there is no overall force on the object, because the sum of all the forces adds up to nothing. And you can tell that because you get back to where you started from. So a closed polygon of forces indicates, I'm going to write this down, a closed polygon of forces indicates an object is in equilibrium. Okay, so far you've now learned that you can move, you can slide vectors about. Okay, so you can slide vectors. And when you're doing addition, the sum is commutative. So addition, oh dear, I can't spell, of vectors is commutative. What that word means is it doesn't matter what order you do. A is B plus C or B plus A. It's the same thing. Okay, so C plus B. Doesn't matter which way around you do it. It's commutative. You still get to the same answer. Right. So we've now discovered one or two extra things about vectors. Commutative. You can slide them about, and the length doesn't change. Oops, the same, and the direction stays the same. Right. I'm going to stop this whiteboard a minute because I want to show you the I'm going to share my screen. Oh, I'm going to go there. I can't remember. In my course, there in the course. Okay. In the useful documents and animations, there's the animations. Oh, I have to log in again. Stay connected, please. Okay, there's my course. I'll try again. Useful documents and animations. Oh, incidentally, I've added in textbooks and notes. So just there's textbooks and notes for all of the different courses. I added that in today. So, but here is the animations, the Walter Fent animations. And if I go down here, we can do addition of vectors. So this is resultant of forces. So here we've got two vectors. I'm going to make that a bit bigger. And we can find out the resultant. That one slides across there. And you can see that we can add one to the other and we get the resultant. Can you see that? And here, if we make this, let's do 4 forces. Okay. Find out the resultant. So we slide that one to there, that one to there. Can you see we're doing tip to toe? Tip to toe. So there's the resultant. Okay. Right, that's the resultant one. If I go back from there and let's go to equilibrium of 3 forces. Let's do this one. Oh no, let's not do that one. Let's wait until we do this one. I want to do resolution of a force into components. Okay. Right, now here we've got a purple force. Let's again make it a bit bigger. So the purple force, it could be any vector, but let's imagine it's a force. The length of this is 5 because we've got 5 newtons. So the length of it is 5, and you can see that it's to the right. Now, I can split that force, just like I did with the black one on my whiteboard. I can split that force into 2 components. One component which is indicated by the red, and the other component is indicated by the blue. Okay, so, and I can set these angles. So this one is 20 and this one is 40. Let's find the components. So I can move that one across to there. And that one goes to there. And can you see the parallelogram of forces? So there is my blue component. And there is my red component. And when I add the blue one to the red one, can you see that this blue one, let's go to blue. This blue one here can move to here. So the red one plus the blue one gives me the purple one. And I could do it the other way. So the blue one and the red one give me the purple one. So now I can split any force into 2 components. What would be a sensible arrangement of components? And the truth is that when we do this in physics, we nearly always split one force or one vector into 2 components that are perpendicular to each other. So if I were to choose angles which add up to 90, so if I leave the blue one at 20, but I give the red one the angle of 70, now my red and my blue components are going to be at right angles to each other. Okay, so I've got, can you see these two are at right angles to each other? If I annotate, that is at right angles to that one. Okay, so I'm splitting my my purple force into 2 perpendicular components. So now, if I find my components, there they are. There's my blue one. And there's my red one. And it's actually put the numbers in here. Okay, let's try and work out the red one. Remember that this purple one is 5 newtons. So this length is 5. Okay, this angle, that one, is 70. And this happens to be, well, it's our parallelogram of forces, but it's a very special parallelogram because it's a parallelogram with 4 right angles. This is a right angle. So now if I change to, let's go pink. Oh no, maybe not. It's too close to the purple. Let's go orange. This orange triangle is a right angle triangle. Okay, I'm going to draw it again out up here so that you can see it more clearly. There is my right angle. This angle is 70 degrees. This length is 5. Oh, that's a rubbish 5. Let's try that again. 5 newtons. Right. So what I want to do is I want to find this side. This side is my red component. Okay. So it's just trigonometry. Can you see that this side is my adjacent? Okay, it's adjacent to the angle for this right angle triangle. So I can say that cosine, because it's adjacent, of 70 is equal to, let's call it, I don't know, P. P over 5, which is the hypotenuse. Can you see I can multiply by the 5 and I end up with 5 cosine 70 is equal to P. Right, now I could use this angle and this right angle triangle at the bottom for the other component. But can you see that that blue arrow is also in this same triangle? This side is the same as the blue arrow. My lines are a bit wibbly, but I hope you can see that. So in the same triangle, my blue arrow, my other perpendicular component, is 5 sine 70. I'm going to call it Q. And I want you to notice that I didn't actually do the proper SOHCAHTOA thing. I just realized that if one of them is the cosine, because it's adjacent to the angle, the other has got to be the sine, because it's opposite the angle in the same right angle triangle. So, and you always multiply by the amount on the hypotenuse when you are resolving into perpendicular directions. And you always get one of them is the hypotenuse cosine the angle, and the other component is the hypotenuse sine the angle. This is a general rule for resolving vectors into perpendicular directions. And we resolve vectors into perpendicular directions really frequently. It happens all the time. So let's give ourselves an example of this, shall we? Okay, I am going to clear my drawings and let's go to, I'm going to stop sharing and give an example of this. So let's go back to my whiteboard again. There it is. Right. Okay, so resolving forces. Resolving vectors. Like I say, we nearly always do it in to perpendicular directions. So I am going to resolve this vector, and I think that it is 25 meters per second. Meters per second. So it's a velocity vector, v. Okay. And what I want to do is I want to resolve it into 2 perpendicular directions because I want to use the vertical motion separately from the horizontal motion, which you can do when you are doing projectiles. It happens a lot. Okay, so oh no, I don't want it to be black. Let's get rid of that. I want it to be red. Red, please. Okay. Red. Right, so here is my horizontal component. I'll try and get it lined up. There we go. And let's do the same again. I want, actually, shall I do it a different colour? Let's do green. I hope I don't have anybody here who's colourblind. There is my vertical component. Okay, and I want you to notice that I can take this component and put it there and it fits. Can you see that? Pardon me. Oh, excuse me. Now what I'm going to do is I am going to draw in this angle. What does that look like? That looks like about 36 degrees, I've just decided. Okay, and because I'm resolving into two perpendicular directions and one of them's vertical and the other one's horizontal, I know that they are at 90 degrees to each other. So there is my right angle triangle. Okay, and so what I'm going to do now is I'm going to find the size of my green vector, which I'm going to call y. Okay, can you see that it's opposite this angle? So it's sine, you multiply by the hypotenuse, so it's 25 sine 36 degrees is equal to y. And just as quickly, this one's x, and you see this is adjacent to the angle. So this one's cosine, so we've got 25 cosine 36 is equal to x. I hope that you can see that it's always going to be like that. We get one of them sine and one of them cosine. Yay! So this is resolving vectors into perpendicular directions. Right, now this is nice. Now the next thing I want to do is I want to do it on a ramp. Okay, because that's the next thing that happens and it's horrible. Right, so where is my thing? There it is. Right, so now I am going to draw a ramp. Oh, it's going to be a green ramp. And here is my floor, my horizontal. And I am going to say that that angle there is, I don't know, 29 degrees. I've just decided. And onto my ramp, I've got an object, a little box. And what are the forces on the box? Can anybody name the forces? This object, it's not sliding down the ramp, it's in equilibrium, it's staying still. And yes, KV, we've got the weight, absolutely. So let's draw it with an arrow. Why not? Okay, so from the center of mass, I'm going to go right the way down so that it crosses this other one because it makes things really clear then. Okay, so there's one of my forces. Okay, I'm going to draw a different force. I need another force. The normal contact force. Well done, Errol. Okay, so the normal contact force is what it says on the tin. It's an arrow that is at normal, the right angles to the ramp surface. Okay, so there is my normal contact force. I need one more force or that object cannot be in equilibrium. So well done, Mikhail. It's friction. And the friction has to oppose motion. Well, it's not actually moving, but it wants to slide down the hill. I hope you can see that there is a component of the weight down the hill. So the friction has to be up the hill. Okay, right now, these three forces, if I were, I'll take them away and show you that you can make them add up to give you, That one's a little bit on the long side. Let's make it a bit shorter. Yeah, about like that. Right, okay. So so here are my three forces. Okay, so this one is the weight. I've called it W. This one is the N for normal contact force, and the blue one is my friction force. Okay, right now I want to resolve into two perpendicular directions, because if the object is in equilibrium, then the forces add up to nothing. Okay, right now let's do it. I could rearrange these forces to give me an arrow thing. Whoops, that it's a closed polygon. Oh, I haven't got that quite right, have I? Look, that needs to be a bit more like that. Actually, let's make that one a bit longer. Come on, longer. There we go. So can you see that those three arrows add up to give you nothing? So this is the condition for a an object that's in equilibrium. The forces add up to give you nothing. There's no net force. Right, I'm going to pop them back in. Oh dear. Okay, so you have to imagine that these three all line up. Oh. Okay, so they all meet in one position. It's meant to be in the middle of my shape, but never mind. Okay, so I've got these three forces, and when I do them tip to toe, they add up to give me a big fat nothing. And the consequence of that is that I end up with a triangle of forces. But what I want to do, so these forces definitely add up to give me nothing. What I want to do, though, is I want to split my weight. And if I do it to the weight, then I only have to split one force. I'm going to split my weight into two perpendicular directions, one which is parallel to the ramp and one which is perpendicular to the ramp. Okay, so I'm going to split my weight into, let's do two pale green ones. So there, that one's parallel to the ramp. And I'm going to do another one there that's perpendicular to the ramp. And can you see that I've got my parallelogram of forces again? Let's duplicate that and pop that one there. And let's duplicate that. And I can pop that one there, except it won't stay. Oh, so annoying. Right. I wish it didn't keep jumping to my dots, but it is. Okay, so there is my parallelogram of forces, my very special parallelogram, which has got right angles because it's a rectangle. And I can name those two components. Okay, I'm going to call this one W perpendicular and this one W parallel. So there's my parallel lines. Okay, because it's parallel to the surface, this one's perpendicular to the surface. Right, okay, so what I want to do now is I want to find, let's suppose we were asked to find N and F, and they gave us W. Let's say that the mass of the object is, I don't know, 5 kilograms. Okay, so the weight is M times G, so it's 5 times 9.81, which gives me, I should have done 10, it's saved me trouble. 5 times 9.81 equals 49. 49. Oh, no, 49 newtons. I put that in the wrong place. Let me just rub that out because that's just wrong. Right. Okay. So, so there is my weight, and what I want to do is calculate N and F. How can I do it? What I've got to do is I've got to resolve W into those two perpendicular directions. Can you see that N has got to equal W perpendicular and F has got to equal W parallel because they've got to cancel each other out completely. So I'm going to write this down. Resolving parallel to the slope. Okay, so this is W parallel. Now I need a triangle that's got an angle in it, and this rectangle with the diagonal drawn in, which is W, hasn't got an angle in it yet. So where can I get my angle? So this 29 gives us, that one's 90. I hope you can see that. So that one's 90 minus 29, which means that that one's got to be 29. So I'm going to use that right angle triangle, that one. Oh, this one. That pale yellow one. Okay, so I'm going to use that right angle triangle. And what do I get? If I just quickly sketch it over here, it's like that, isn't it? Oh, sorry. There's my right angle. This one's W. That's my 29. This is W perpendicular. This one's W parallel. Okay, so, and that's separate. Oh, that's a bit of a tight squeeze there. Right, so can you see in this right angle triangle, W perpendicular is adjacent, W parallel is opposite my angle. So opposite is sine. So again, multiplying by the hypotenuse, I get 49 sine 29 equals W parallel. And because up and down the slope there's got to be 0 force, W parallel equals F. So that is equal to F. So if I do 49 times sine 29, I get F is 23.8, 24 newtons. Okay. Now, if I want to do the same, but for perpendicular. Okay, it's exactly the same triangle, but the perpendicular one, can you see, is adjacent? So it's 49 cosine 29 is equal to W perpendicular. And because it's gone off the top, but because W perpendicular has to match the N, that is the same size as N. So 49 times cosine 29 gives me N is equal to 43 newtons. Okay, so resolving parallel and perpendicular to the slope is a powerful thing to do. You just need to be a little bit careful where you put your angles, and then you can equate the forces so that you can find the answers that you want. I hope that that covers most of what you have to do with vectors in year 12. So what I was thinking I might do now, unless you've got some questions, please pop them in the chat. I thought we might move on to do some questions. So let's close the whiteboard and share my screen again. Go back to my course platform, and in the maths for physics, we've got maths questions by topic, and we've got scalars and vectors. And I did one of these on Monday in a catch up and it was horrible. So I'm going to pick a different thing. So we're going to do this one. Oh, somebody sent me a chat. What's that? You don't understand how the triangle angle is 29. Right, I'm going to do that again because that is difficult. Okay, it's something that comes up over and over and people don't understand. So we're going to do it again. There's my weight. That one's 29. My W is resolved into W parallel, W perpendicular. Right, Ludan. That is a right angle because this is the horizontal and weight is always vertical. So that has to be a right angle, which means that that angle, because this is a triangle, that angle has to be 90 plus 29 plus that equals 180. So that has to be 90 minus 29. Okay. But W parallel and W perpendicular are at right angles to each other. So I'm going to change color. That is 90 degrees. This bit of it is 90 minus 29, which means that that angle has got to be 29 degrees. So when you draw in your rectangle, that is a right angle. That angle is 29 degrees. Do you understand where it comes from now, Ludan? Yay! It's just a little bit of geometry. Yeah, it takes, you've got to get used to doing this though. Either that or you just have to remember that the angle of the ramp is the angle between W and the perpendicular. Okay, it comes up a lot. Okay, I'm going to clear those drawings because we're going to go on to question number 1. It says the figure below shows a heavy mirror hanging symmetrically from a nail fixed to a wall. It's supported by a strong cord attached at 2 points on its top edge. Draw and clearly label 3 arrows. So this is what I was saying. Draw a diagram. I mean, they're telling you to. So you'll get 3 marks, 1 for each arrow. Right, now, one assumes that the mass of the picture is going to be in the middle. It really needs to be directly below the suspension point, and the weight goes straight down. You should draw it with a ruler. I didn't, but you should. So there's one force, the tension in the string there, and that tension in the string there. Oops. Those two. The components of the tension don't count. No, right. They asked you to draw 3 arrows showing the forces, right? The tension in the string is where the force acts. Okay. Yes, we can replace it with components, but the components aren't the force. Okay. Yeah, they're equivalent, but they're not the force. Okay, so the force goes along the string because actually the force is transmitted by the positive and negative charges of the atoms in the molecules that make up the wire. Okay, so the forces act along the wires. Okay, I want you to recognize that these 2 forces that I'm drawing really scruffily, they have to be the same size, but they're not the same force. Why not? Because they're in different directions. They do have to be the same size. And I know that they have to be the same size because the angles are the same. Plus, the tension on a string is the same everywhere, assuming no friction where it goes over the hook. Okay. So, and of course, we always assume no friction unless they mention it. We always assume no air resistance unless they mention it. So, you know, it's spherical chickens in a vacuum. You have to make assumptions in order to make these questions doable. Okay, so I'm going to call this one T1 and I'm going to call this one T2. But can you see the size of T1 and the size of T2 must be the same? Okay, because it's the same angle and the horizontal components have to cancel each other out. Otherwise, this object would be moving. Okay, would be accelerating. So those are my 3 forces. Okay, and then it says the tension on the cord is 39 newtons. So this is 39 newtons, and this is also 39 newtons. Okay, it says the angle that each end of the cord makes with the horizontal is 40, and you can see there is the 40. It says calculate the vertical component of the tension in the cord, and hence the weight of the mirror. Okay, so that's what we're going to do. We're going to say that, let's go paler so you can see it on the black. We're going to say that we're going to resolve vertically. And we need to do it vertically because there is no component of W in the horizontal direction because it is totally vertical. Okay, so we can split T1 into a vertical component and a horizontal component. And we can split T2 into a vertical component and a horizontal component. Okay, T1 and T2 are the same size, so the vertical component of each of them is the same. Okay, I'm going to redraw one of those arrows. So there is T1, and here is my vertical component, and here is my horizontal component, and there is my 40 degrees. Can you see that T vertical is the same there as there? T vertical, there is my 90 degrees. There in green, that is my right angle triangle. Okay, I want the vertical component, it's opposite my angles, so it's sine. So T1 is 39, so it's 39 sine 40 is equal to T vertical. Okay, but can you see that I've got two of them? Because I've got T vertical there and T vertical there. And those two upward forces have to equal my downward force in order for there to be no overall vertical force. So 2T vertical is equal to W. So I've got my pictures in the way, so I'm going to come down here. I'm going to say 2 times, and T vertical is 39 sine 40 degrees equals W. So now I can put my numbers in, and I can say 2 times 39 times sine 40 degrees, close my brackets, and I get W is equal to 50.1 newtons. Okay, the vertical component of the tension is this one. We didn't actually work it out. Let's do that. So 39 times sine 40. So this is just one component, just one, and it is 25 newtons because this one is 50 newtons. And we've got two of those, remember? Okay. I hope that you can follow this. Please ask away if you don't understand. Okay. So clearing those ones, I'm going to move on to the next question. Right. Complete the following table stating whether the quantity is a vector or a scalar and give the unit. The full name of its, okay, full name of the unit. Right, displacement, vector or scalar? Anyone? Yay, well done, Nadia. So that's a vector. What's the unit for displacement, please? This is the SI unit, the Standard International. It actually stands for Scientifique Internationale. It's a French thing. Yeah, it's a little m. A big M technically means mega when it's applied to units. So it's a little m. It always really annoys me when people say little m after a number of pounds, big, and they mean million pounds. It's not. It's a big M if it means million. But anyway, very annoying. Okay, kinetic energy, vector or scalar? Scalar, well done, Errol. Okay, so that's a scalar. What is the unit for kinetic energy? Yes, joules, well done. Okay, capital J, because he was a man, so he gets capital letter. Right, power, vector or scalar? Scalar, well done. Okay, let's just think about this. So the definition of power is energy divided by time. Neither of those are vectors. And power certainly doesn't have a direction, does it? So it is a scalar, okay? Units for power, the SI units for power, watts, well done. Okay, again, capital W, because he was a man, it's a proper name, so it gets a capital letter. Okay, good. Brilliant, brilliant. We're doing really well. Right. Let's move on to this one. So now what we're doing is we're going to be combining velocity vectors. Okay, so the figure below shows a river which flows from west to east. So I think that this is the river. This is the river. So I need to, yeah. So this is my river. Woo! And it's going that way. Right. So there's my river. Okay, and it says that the velocity vector for the river is 0.5 meters per second. Okay, so let us draw in. I'm going to draw in my my velocity vector. It's in blue. Okay, there it is. Right, then it says, "Woo, go away." It says a small motorboat leaves the south bank heading due north at 1.8 meters per second. Find by scale drawing or otherwise the resultant velocity of the boat. Okay, so we could do it by scale drawing. What I'm going to do first is I'm going to let's do an upper arrow. So can you see that if we were to add them, that one's 0.5, so 1.8 is actually bigger. More like that. Okay. Find by scale drawing or otherwise the resultant velocity of the boat. So can you see that we would do, if we were going to do it by scale drawing, we would have to make this one, I don't know, 50 centimeters or 5 centimeters long. Let's make it 5 centimeters. And so you need to multiply this by 10 in order to get it in centimeters. So we multiply this by 10, we get 18. So this one would have to be 18 centimeters long. Okay. And then tip to toe, the resultant would be there. So that one would be the resultant right now. Can you see that there is my right angle? I've got these two sides. How do I get this length? Remember that the size of that vector gives us the velocity of the boat. What do we do? Pythagoras. Perfect. Well done, guys. Okay, so our velocity squared is equal to 18 squared plus 5 squared. So our velocity is the square root of that. 18 squared plus 5 squared, all square rooted. Let's do that. 18 squared plus 5 squared. And we're going to square root it. And I get 18.7 meters per second. That is the size of my velocity. Now, can you see they've given you a really big hint here? A vector needs two numbers to define it. We've got the length of that arrow, but we also have to decide on the direction. Okay, so can you see that we've got north? Now, normally when you're doing bearings, you're measuring the angle between the direction you're going and north. Okay, so can you see that if I put in a line which indicates north there, the angle that I want is, let's do it in green so it's easier to pick it out, is that one. That's the angle I want. Can you see that it's the same size as that one? I hope you can, because that's parallel to that, and that's a line that's crossing the parallels, and so that angle is the same as that angle. I hope you can see that. That's just basic geometry in our maths thing. Okay, so here is our right angle triangle. We want, I'm going to call it angle X. Okay, how do I get X? Well, rather than make a mistake and get the hypotenuse wrong, let's just do tan, because we've got the opposite and the adjacent. So I can say that tan X is equal to opposite over adjacent. So it's 5 over 18. So X is equal to tan. Oh, have I done something wrong? Oh, you're quite right. Okay, tan to the -1 of 5 over 18. The angle will be the same. You're absolutely right. Well done. Errol, you get a star. Hang on, let's just do my tan thing. Right, shift tan 5 over 18. And I get, this one's 15.5. Right, that's degrees. Right, you're absolutely right. Right, now I used the sizes of my centimeters. So I haven't, this is now to scale, isn't it? So I multiplied the 1.8 by 10 to get 18, and I multiplied the 0.5 by 10 to get 5. So now I've got to divide this. So you're absolutely right. I've made it 10 times too big. You're brilliant. Well done, Errol. Absolutely brilliant. I'm so glad that you spotted that I made that mistake. So it isn't 18, it's 1.8, and it isn't 5, it's 0.5. Okay, so yeah, so it's 1.8 squared plus 0.5 squared, and then I have to square root that, and I get the same, well, it's the same thing, but it's divided by 10. So this becomes 1.8. So, and I need now to rub that out. There we go. So 1.87. So brilliant. Well done. Very, very good. That's 1.8. That's 0.5. So I'm sorry that I hope I haven't confused anybody. So you would do the 18 and the 5 if you were doing the scale diagram, and I forgot to then unscale it at the end. See you soon.